We're now completing our section on thermodynamics, and this chapter 19 on thermodynamics. The first thing we need to do is discuss the four laws of thermodynamics and then describe some terms that we'll be using later. As you can see, the zeroth law is an afterthought. There are actually four laws: the first, second, third, and not the fourth, but the zeroth. The zeroth law, as I said, an afterthought. It was realized that if two systems are in equilibrium with a third system, then they are in equilibrium with each other. And this zeroth law was found to be necessary because it could not be derived from the other laws of thermodynamics. So, for example, if we have a system A and a system B, and they're in equilibrium, what does that mean? It means that no heat passes from one to the other. So basically, in common terminology, this means that A and B are at the same temperature. So if A is in equilibrium with B, and A is also in equilibrium with C, then it turns out that B will be in equilibrium with C. So if A and B are in equilibrium and A and C are in equilibrium, then B and C will be in equilibrium, that is, have the same temperature. The first law of thermodynamics is that the internal energy is equal to the heat gained minus the work done. Well, if you think about it, this is kind of common sense. It's the law of conservation of energy. So the first law is the law of conservation of energy. And it basically says that if we have some system here, and if we look at the total internal energy, which is going to be the total random energy, usually kinetic, but it could be potential or rotational or whatever. This is the term that we've previously used as U. Kind of like the temperature is a measure of the average random kinetic energy. So we take that average random kinetic energy and multiply, you'll recall, by the total number of molecules to get the total random internal energy. This total internal energy will be increased if heat is added less the work that the system does. So if heat goes in, Q, which is normally used for heat, and work comes out, then we'd say that the change in the internal energy, I don't have it here in the form of an equation, but the change in the internal energy is going to be equal to the heat in minus the work done. Now, why is it expressed in this kind of strange way? And the answer to that is the early work in the 1800s on thermodynamics used the steam engine as the primary concern of thermodynamics, because this was a way that we could get energy out of substances such as wood or coal. And if you take a boiler, like for a train, and you had a fire built under it and the water would boil, and of course the steam would come out and the steam would do work. And so what you did was you put coal in. In other words, you put coal in to stoke the fire, and the fire gave the heat, or Q, to heat the boiler. Now, when the boiler got heated, then work would come out because the steam would push a piston. The piston would be attached to a wheel. This is a poor diagram, but it gives you the idea. So the steam would push a piston, the piston would turn the wheel, and work would be done. The train would move. And so the whole concept behind this was we put in heat and we get work out of it. You can't get all of it. Can't get all of this energy, as we'll find out very soon. But this is basically saying energy in minus energy out is going to be the change in energy. The change in energy, this is basically the first law of thermodynamics. The second law of thermodynamics says that heat flows from a higher temperature to a lower temperature and never conversely. Or we could say equivalently that the total entropy or disorder always increases for an irreversible process. Let's look at the second here. Second law of thermodynamics states that if we have a hot object and we have a colder object, then heat is always going to flow in this direction, and heat will never flow in this direction. And that's, of course, that's common sense. If it could, then cold things could heat hot things up hotter and hotter and hotter. However, when we say that the heat goes in this direction, what we're really saying is this random thermal motion here hits these molecules which are moving more slowly, and it preferentially will make them move faster. So heat goes over here, but that also removes the random energy from this side and puts it into this side. So this side gets warmer, this side gets colder, until finally we have a situation of equilibrium. And that equilibrium, after that equilibrium is achieved, we don't know which side was the hot and which side was the cold. In fact, the disorder that is increased here, or the entropy, is an irreversible process. And that's why we can't go from an orderly process like both sides being the same to one side suddenly pushing heat into the other side if they're in thermal equilibrium. So we get our first evidence here that entropy or disorder always increases for an irreversible system. The entropy is constant if the process is reversible. And we do have many processes that are reversible. The simplest is cyclic motion, like a planet going around the sun if there were no tidal forces. That's a cyclic motion. Something's happening, but it's not losing any entropy or disorder. The third law is that if we have a system, it's not possible to lower the temperature down to absolute zero in a finite number of steps. So if we have, no matter how cold this is, it's something above absolute zero, temperature greater than zero, we can take a certain amount of energy out, but you can never extract all of it. It takes an infinite number of steps, and you can take some energy out with each step by finding something that's colder than this, or by allowing this process to deteriorate where the entropy is lowered and lowered and lowered so that finally we get a temperature closer and closer to absolute zero, but never at absolute zero. And that's just not possible. Okay, now some terminology that we need to discuss. The first of these terms is isobaric. And iso means the same, and baric refers to pressure. And so an isobaric process is one where there is no change in the pressure. Isobar is a line of equal pressure. And you may remember from maps of the United States, although this is kind of crude, that you would see pressure, like for a high pressure here, and then maybe a low pressure here. And as we looked at these different pressure lines, if we followed this line around here around this high pressure center atmospherically, we would find that the atmospheric pressure was the same here. P was constant. And so we call this an isobar, and this is an isobar. So you're surrounding yourselves with isobars, kind of like equal elevation around a mountain. This would be one that would pass between the two of them. And as you probably realize, if I have a situation where I have a high pressure and a low pressure, then in fact, if I have a lot of lines very close together, this results in very strong winds and air currents between the two. If the pressure is not changing very much, then I do not have that pressure to create winds. Isothermal is the next one, isothermal. And you're also familiar, or again draw the United States. Didn't quite do justice to Florida and Texas there. But if you'd look, say, at different times, you might find isotherms And an isothermal process is one where the change in the temperature is zero, no change in temperature. So these are isothermal lines. This might be 70 degrees, 80 degrees, and 90 degrees Fahrenheit. And as you move along that line, it's an isotherm, and so the temperature is exactly the same at all points on the line. It's a very fast way of getting an image of what is happening. And you might have, something unusual like a curve here for 60 degrees up in Canada. So that's an isothermal line. And you can see these examples with weather maps. The next one is iso, again, meaning the same, choric. And this is something you may not have heard. It is the same as isovolumetric. It means that there's no change in the volume. The volume is equal to a constant. We don't see that in weather maps, but we do have that with objects. For example, a closed sealed container, like a Coke bottle, has a constant volume inside because the volume can't expand or contract. On the other hand, if you have a balloon, the volume can expand or contract inside the balloon based on the temperature and the pressure. So an isochoric process is one where the volume is constant. Finally, the last one we need here is what we call an adiabatic process. And an adiabatic process is one where the change in the heat is equal to zero. In other words, there's no change of heat, there's no heat that enters, and there's no heat that leaves the process. And these are the four terms that we'll use again and again. Same iso pressure, same temperature, isothermal, same volume, and same heat. In other words, heat doesn't enter or leave the system. The volume doesn't change, the temperature doesn't change, the pressure doesn't change.